let us proceed Buttress dam example. So this is the example 2.3. The profile of the major monolith of Buttress dam is shown below. The stability of the dam is to be reviewed against overturning, where if not must be more than 1.5, and against shear friction factor must be more than 2.4. So assume the following characteristics, just concrete characteristics, this characteristics, and analyze the static stability of Buttress with respect to plan XX, which is the base contact. So you have two cross sections you can see. So you have plan view. This is a single Buttress plan view. So you have dimension. So let us see. Second problem is determine the prestress load required in each unit. In each unit, considering seismic criteria for FSF must be 3.2. So I think you have to divide this cross section into three portions. Portion A, just above design flood level, this rectangular portion, just to calculate self weight, and B, this one, this rectangle up to the base contact, and C, this triangular portion. Now let us see. So you have a single Buttress unit, you have 10 meter width to this direction. So the hydrostatic pressure is acting like this. So you have triangular portion, it will act up to 10 meter distance. So analysis must be done for a single Buttress width. It is not like a gravity dam per 1 meter dimension. So let us see. Solution, normal combination NLC, water load to design flood level, DFL, and also self weight and uplift pressure, which is no pressure relief. So no uplift pressure, or just uplift is insignificant, so no drainage gallery. So I think you can see now, this is hydrostatic pressure, the first one. So since it is triangular portion, you can see triangular portion Z1 and gamma W Z1. This is the distribution of hydrostatic pressure. So you can see now, if you multiply area, half times gamma W times 10 times 20 square. 20 square. 20 is the height of water. So Z1 times Z1, 20 square. And also 10 meter width to this direction. So that's why 10 square. Clear? Gamma W times 10. So you will get 20,000 kilonewton acting at 20 over 3, which is 6.66. Okay, second one is water load. This is just the inclined portion. So you have PWV, which is a vertical water load acting on this sloping face. So you can just calculate PWV. Similarly, you have triangular portion, 2 meter dimension to this direction. Then you have 20 meter. So once you calculate this dimension, then you can get automatic result, which is 1 over 2 gamma W times 2 meter width times 20 depths, then times 10 meter inside, just 10 meter width of single Buttress. So if you multiply 2000 kilonewton acting at 19 minus 1/3 of 2, which is 18.33, which is this one. 19, how do you get? You have 16, then 3 meter, then 19. So this is triangular portion on the top. This is triangular portion. So if you subtract, you can get the centroid of this PWV, which is at 2/3 of at 1/3 of 3. From 19 you are subtracting just 16 plus 3, 19 means up to this. So you have triangular to this direction, you get 1/3 of 3, then 18 meter. So let us go to self weight of the dam. So you have portion A, gamma of concrete is 23, then 23 times 10 times 10 times 2, you have the 3 meter, 3 meter this one, then 2 meter height, 22 minus 20, 2 meter. So height times width times internal width, which is 10 meter. So you have this one, you get this acting at 15.5. How do you get 15.5? Start like this. So you have, this is a triangular portion. So if you have 20 meter depth with this side slope, 1 vertical, 0.7 horizontal, then if you go 20 vertical, what will be the horizontal distance, which is 14 meter. You have 14 meter here. So you have 14 meter here. So you go to this one, this is the portion. You have 3 meter dimension, since it is rectangular, 3 over 2, 1.5. So 1.5 plus 14, it will give you 15.5 meter, 1.5 you add. Okay, second one is cross-section V, which is this one, 10 times 20 times 3. Where you have 20 depths, 20 meter depths, you have 20 meter depths, Then you have again, you have 20, then times 3. So you can see 3 meter distance, 3 meter total width of this one. So 20 meter height times 3 times 10 meter inside to this direction. So you calculate, then the centroid will be 16.5 meter. How do you get? You go to this cross section, you have 16 up to this point, 16. So total is 3 meter. So half of this 1.5, then 1/3 of this, 1/3 of 1.5, 1/3 of 1/3 of 1.5, it will give you 0.5. So 16 plus 0.5, 16.5. This is the centroid from the top of the dam. So this is the top of the dam from this distance. Okay, so you have C, cross section C. Similarly, you can see cross section 3. This is triangular portion. So you have total area. You can multiply 23 times 10 times 3 times 16 times 16. So you have 16. This is 16. Then you have 16. Then times 3 meter. This one. 3 meter width. Then you have height. Then automatic you will multiply. So just like this. So we are calculating below this one, below the vertical point. So 16.5, then 10 meter. Centroid already given by composite area meter. You can calculate this small triangle here, and this is the right angle. So the two triangles composite area from the top of the dam, you have 10 meter. So if you multiply this one, you get moment. How do you get? Just multiply. Let us see the table. Let us see the table. This is the table, load moment table. So you have water load, moment arm you have to put. So this is just horizontally negative, which is hydrostatic pressure, then negative moment. If you multiply negative moment, you get vertical also, vertical water load. Already you have calculated moment arm. Then this is positive, downward direction. So you have moment positive. Similarly, uplift, I think it is insignificant, but you can calculate. Uplift again, you can calculate 10 times 1/2 gamma w z times ts. So 1/2, which is just this one, Buttress head. Uplift is distributed on Buttress head only. Let us see. This one, on Buttress head only. Gamma w times z1, you have this dimension, which is 3 meter. Then internal dimension to this direction, 10 meter. So if you multiply, automatic you get uplift again here uplift, which is 3000. So 1/3 of 3 or 18 meter already we have calculated. Okay, so but this uplift is negative, direct negative vertical. So you have this moment. Then A, B, C, similarly you have to put all resisting forces, then positive moment. So let us go to the calculation now. So please just see this one, visualize this buttress dam. So this is to just you have a parapet wall also, inspection gallery sometimes installed. So uplift is just acting just on buttress head only. Uplift is acting on buttress head only. That's why gamma w z1 times this dimension 3 meter, then internal to this direction you have 10 meter. So I think this is important. That's why reduce advantage of reducing uplift pressure. So let us go to F node, overturning stability. This equation, sigma moment positive divided by sigma moment negative. So if you divide, you get to 0.11. So this means satisfactory, which is safe. It is more than 1.5. Okay, shear friction. Okay, resistance to sliding and shear divided by summation of the horizontal forces, which is net force. So if you go to this one for horizontal foundation, you have this resistance to sliding and shear, cohesion times area of the base plus sigma v times tan phi over sigma h. So you get 2.833. So this is also more than 2.4, satisfactory. But area of the base, how do you get? Just the area of the base, simply multiply this one. You have 10 times 3. This is 10, then times 3 meter dimension, 3 meter dimension plus this one. You get what? Area of the base contact this one for a single buttress. So 78, this is just area of the base. So once you get this one, then you go to this one, seismic criteria for shear friction, which is unsatisfied because 2.83 is less than 3.2 if you consider seismic criteria. If the area is suspected to earthquake action. So prestress load per buttress, which is design prestress required for sliding, can be computed by the tendons if the tendons are inclined. So you have this equation, you know this equation, you have once shear friction. If you fix, then what will be the design prestress required for sliding? So substitute only. So once you substitute, you get the sliding design prestress required PPS 7,230 kilonewton per buttress. For each buttress, you need this kilonewton tendon. So you have two prestress tendons per buttress. So if you divide by 2, you get this one per tendon. So you need this amount of force to just resist the overturning moment, so that the dam structure will be stable. So further, you can calculate overturning design prestress required. So PP naught, you can calculate again using this equation. So you get this one, kilonewton per meter. This is kilonewton per meter. So you have how much? 10 meter distance. So for 10 meter per buttress, you need this amount, which is just counterbalancing positive this positive 504.971 kilonewton to the counterclockwise direction. You have to apply so that the buttress dam will be stable. So this is a buttress dam, just a picture, you know, downstream side. So these are holes, but connected with struts or some reinforcement bars, which is highly reinforced cement concrete. So it is connected. So that's why saving of concrete volume. But in concrete gravity dam, this all filled. So single buttress connected each by strut or by strut and other RCC structure. So you can see, just visualize the dimension and other. It is very simple. So I think this is the example for buttress. If you have any question, you are welcome. I think you can just send via Telegram or website or email address. I think if you have any question, you are welcome. Okay, stay safe and healthy. Let us protect COVID-19 together. Okay, thank you.